Preventive techniques. There are a number of common techniques that help avoid potential reentrancy vulnerabilities in smart contracts. The first is to use the built-in transfer function when sending Ether to external contracts. The transfer function only sends 2300 gas with the external call, which is not enough for the destination address/contracts to call another contract. In other words, re-enter the sending contract. The second technique is to ensure that all logic that changes state variables happens before Ether is sent out of the contract or any external call. In the Ether store example, lines 18 and 19 of etherstore.sol should be put before line 17. It is good practice for any code that performs external calls to unknown addresses to be the last operation in a localized function or piece of code execution. This is known as the checks-effects interaction pattern. A third technique is to introduce a mutex, that is, to add a state variable that locks the contracts during code execution, preventing reentrance calls. Applying all of these techniques to etherstore.sol gives the reentrancy-free contract. Using all three is unnecessary, but we do it for demonstrative purposes. Function, withdraw funds, with one parameter, uint256, underscore way to withdraw, public. Open brace, require, negation of reentrancy mutex. Require, balances of message.sender is greater than or equal to underscore way to withdraw. Require underscore way to withdraw is less than or equal to withdrawal limit. Require, now greater than or equal to last withdrawal time of message.sender, plus 1 weeks. Balances of message.sender minus equals underscore way to withdraw. Last withdrawal time of message.sender equals now. Code comments. Set the reentrancy mutex before the external call. Reentrancy mutex equals true. Message.sender.transfer of underscore way to withdraw. Code comments. Release the mutex after the external call. Reentrancy mutex equals false. Close brace. Real-world example, the DAO, Decentralized Autonomous Organization. The DAO attack was one of the major hacks that occurred in the early development of Ethereum. At the time, the contract held over $150 million. Reentrancy played a major role in the attack, which ultimately led to the hard fork that created Ethereum Classic, ETC. For a good analysis of the DAO exploit, see the Analysis of the DAO Exploit page. More information on Ethereum's fork history, the DAO hack timeline, and the birth of ETC in a hard fork can be found in the Ethereum standards section. Arithmetic over/underflows. The Ethereum virtual machine specified fixed size data types for integers. This means that an integer variable can represent only a certain range of numbers. A uint8, for example, can only store numbers in the range 0 to 255. Trying to store 256 into a uint8 will result in 0, if care is not taken. Variables in Solidity can be exploited if user input is unchecked, and calculations are performed that result in numbers that lie outside the range of the data type that stores them. For further reading on arithmetic over/underflows, see How to Secure Your Smart Contracts, Ethereum Smart Contract Best Practices, and Ethereum, Solidity, and Integer Overflows, Programming Blockchains Like 1970. The vulnerability. An over/underflow occurs when an operation is performed that requires a fixed size variables to store a number or piece of data that is outside the range of the variable's data type. For example, subtracting 1 from a uint8 variable whose value is 0 will result in the number 255. This is an underflow. We have assigned a number below the range of the uint8, so the result wraps around and gives the largest number a uint8 can store. Similarly, adding 2 to the 8th equals 256 to a uint8 will leave the variable unchanged, as we have wrapped around the entire length of the uint. Two simple analogies of this behavior are odometers in cars, which measure distance traveled. They reset to 0 after the largest number, 99999, is surpassed, and periodic mathematical functions. Adding 2π to the argument of sign leaves the value unchanged. Adding numbers larger than the data type's range is called an overflow. For clarity, adding 257 to a uint8 that currently has a value of 0 will result in the number 1. It is sometimes instructive to think of fixed-sized variables as being cyclic, where we start again from 0 if we add numbers above the largest possible stored number, and start counting down from the largest number if we subtract from 0. In the case of signed int types, which can represent negative numbers, we start again once we reach the largest negative value. For example, if we try to subtract 1 from a int 8 whose value is negative 128, we will get 127. These kinds of numerical gotchas allow attackers to misuse code and create unexpected logic flows. For example, consider the time lock contract in timelock.sol. This contract is designed to act like a time vault. Users can deposit Ether into the contract, and it will be locked there for at least a week. The user may extend the wait time to longer than 1 week if they choose, but once deposited, the user can be sure their Ether is locked in safely for at least a week. Or so this contract intends. In the event that a user is forced to hand over their private key, a contract such as this might be handy to ensure their Ether is unobtainable for a short period of time. But if a user had logged in 100 Ether in this contract and handed their keys over to an attacker, the attacker could use an overflow to receive the Ether regardless of the lock time. The attacker could determine the current lock time for the address they now hold the key for, since it's a public variable. Let's call this user lock time. They could then call the increased lock time function and pass as an argument the number 2 to the 256 minus user lock time. This number would be added to the current user lock time and cause an overflow, resetting lock time of message.sender to 0. The attacker could then simply call the withdraw function to obtain their reward. Let's look at another example, this one from the Ethernaut challenges. Spoiler alert. If you have not yet done the Ethernaut challenges, this gives a solution to one of the levels. This is a simple token contract that employs a transfer function, allowing participants to move their tokens around. Can you see the error in this contract? The flaw comes in the transfer function. The required statement on line 13 can be bypassed using an underflow. Consider a user with a 0 balance. They could call the transfer function with any non-zero value and pass the required statement on line 13. This is because balances of message.sender is 0, so subtracting any positive amount, excluding 2 to the 256, will result in a positive number, as described previously. This is also true for line 14, where the balance will be credited with a positive number. Thus, in this example, an attacker can achieve free tokens due to an underflow vulnerability. Preventive techniques. The current conventional technique to guard against under/overflow vulnerabilities is to use or build mathematical libraries that replace the standard math operators addition, subtraction, and multiplication. Division is excluded as it does not cause over/underflows, and the EVM reverts on division by 0. OpenZeppelin has done a great job of building and auditing secure libraries for the Ethereum community. In particular, its SafeMath library can be used to avoid under/overflow vulnerabilities. To demonstrate how these libraries are used in Solidity, let's correct the time lock contract using the SafeMath library. The overflow-free version of the contract is as follows. Contract time lock, open brace. Using SafeMath for uint. Function increase lock time with one parameter, uint256, underscore seconds to increase. Lock time of message.sender equals lock time of message.sender.add seconds to increase. Notice that all standard math operations have been replaced by those defined in the Safe Math library. The time lock contract no longer performs any operation that is capable of under/overflow.